Well, hello friends. Today we are going to investigate something. So I noticed when I made my July update video that when I was showing off the stacks in the process manager and I looked up the Windows server, then there was this thread in there that had died but like was still persisting. And it was so there's a thread that runs when we set a wallpaper because we don't want to block the whole system while we decode an image. So let me grab one of these. We'll use sunset retro.png. It's a thread running, decoding that image. And now, if we look here in the Windows server, we can see that thread 2 here, and the threads are jumping around in this view here, which is also annoying. Would be good if they didn't do that. But yeah, so here is thread 2, and it's the compositor set wallpaper thread, and then it has called the exit thread syscall, and then nothing. So that isn't right. I should do something about that. I guess we gotta investigate what the issue is, because I think that the thread exits just fine. It's just that it doesn't clean up after itself, but I'm not really sure what's going on, so let's go look at the exit thread syscall. So here's what it does. First, we turn off interrupts, and then if this is the main thread it's calling exit thread, then we just turn it into a regular exit syscall. Just to be nice, because unlike other operating systems, in Serenity we actually distinguish between the main thread and secondary threads. So like the main thread is thread 0, and then everyone else is like 1 through in 32 max or whatever. And it's just something that always annoyed me in other systems, that your main thread could be any of your threads. So here, it's built into the kernel. Like the kernel knows which one is your main thread, and the main thread is the first thread to start, and it's just logical that the kernel would know that. Anyway, so but if it's not the current thread calling exit thread, then we set the current thread's state to dying, and then we unlock the big lock. So the big lock is what protects it protects us from entering the kernel from multiple threads at the same time in the same process. So in one process, only one thread can be in the kernel at the same time. It's a limitation that in the future we might try to avoid, but right now it makes building the kernel a lot easier if we can just have this as an invariant that there's only one thread of each process in the kernel at any one time. Okay, so then it unlocks the big lock, and then finally we call big next and switch now, which is basically means that this will never be reached. So this is like bye-bye at this point. Now, the fact that we set this thread state to dying means that somebody should find this thread. So let's see, dying, blah, blah, blah. So usually when threads move into the dying state, then the finalizer process will wake up and go and destroy that thread and eventually move it to dead state. So let's see, dying, dying, dying. Where's the finalizer? Here's the finalizer. Finalizer is a very, very simple little task. It's just this loop here. So we call finalize dying threads, which is this. So for each in state, so it's for each thread in state dying, we add it to the dying threads list, and then we call finalize on them. Okay, and then finalizing thread. So we should have gotten a finalizing thread Did we get that? Finalizing process. No, we never got finalizing thread for the Windows server thread. Well, that's interesting. So why is that? What I normally like to do at this point in time is go in the scheduler code here and just enable this, which one is it? Schedule runnable debug? Yeah, so this one will like print out all the dang time if it didn't bit rot. Shit, this has bit rotted. For each non-runnable and for each runnable. What's the new convention of doing that? Oh, a scheduler for each runnable. Yeah, that's indeed the case. We moved the runnable lists to the scheduler, so they're no longer in the thread class. It's like, I often find that I can review someone else's code and integrate it, and I understand what the code is doing, but like these little details, like this responsibility of like maintaining the list of runnable threads is now moved from the thread class to the scheduler class. This type of information sort of falls out of my head very quickly after a code review. So it's extremely good for me to come here and like have to interact with this code, because it means that now this will be cemented in my head. So yeah, right. So this debug option is extremely spammy, as you can see. But hopefully at some point we will get to a usable GUI. Please. Wonder what he's doing. All these runnables. So yeah, it says the Windows server is running, probably decoding the wallpaper. Oh man, this is just taking so long. It would be nice if I could switch this on when I want it to, rather than having it on all the time. Maybe we should implement that. Okay, so now let's set a wallpaper. So which ones? I have to cheat and look because I don't remember the names. Okay, so let's use brave.png. So now actually we should be able to see here that there's a Windows Server secondary thread, this guy right here. Or no, here even, number 2. So there are 3 threads in the Windows Server right now. This one is presumably the wallpaper PNG decode thread. Non-runnables. Windows Server. He's dead. Oh, well, okay, so we have the wallpaper set now. And what is the state of everything? Non-runnables. This guy is dead. Thread state dead. So who sets that? Finalize. So presumably we are finalizing this thread. But then who's going to clean it up? I guess nobody is going to clean it up. So when we finalize a process, then where did we take care of the threads? Finalize dying threads. Okay, we call finalize in all of them, and then process finalize. Where did we kill the dang? Is it in process destructor? Okay, so it's not until the process Destructor that we actually delete threads. Well, that ain't right. We can do better than that. So let's see, thread finalize. So here, the thing is that when we finalize the main thread for a process, that's when we tear down that whole process. But if it's not the main thread, then we can just tear down this thread, I think. So finalize is should only be called from the not this guy, from the finalizer. So here we are in the finalizer task. And maybe we should assert that actually. Current process, or even assert that current is g finalizer main. Wait, what is the finalizer? Is that a process or a thread? It's a thread. Oh, that's easy enough. I can assert that here too. This is actually a very healthy assertion, I think. Because the whole point of the finalizer thread and having it as a separate thread is so that we can run the destructors on a thread or a process object without having to be either in that process or in the scheduler or in some like unrelated process that doesn't want anything to do with the thing that's being destroyed. So instead we have this dedicated thread called a finalizer thread, and he takes all the responsibility for running destructors. And then it gives us like a very clean operating room or whatever, where we know that we're always in the finalizer thread when we are tearing things down. So it's been good so far to do things this way. So if it's not the main thread that we're finalizing, then let's just delete it. Delete this. Oh, I think yeah, because here we're just iterating over a vector of the dying threads. There's nothing else to do after this point. So let's try it. Oh, and let's do it without this gunk. So we can actually get somewhere today. Okay, so was it sunset retro.png? It's a little sluggish while you're doing that, I have to admit. And Windows Server, come here, and stacks. And thread 2 is gone. Okay, so now let's load another one. Not braid PNG. We got thread 3 there, and then and everything comes back to normal. Sort of. It looked like thread 1 was gone for a moment, but I think that was just a glitch. Because it wouldn't make any sense if the thread 1 would disappear. Thread 1 is this thing up here. It's always updating the CPU usage monitor. Let's see. It's just a repaint glitch of some kind, yeah. Not good to have repaint glitches, but still. So I think that we have solved the problem of the thread not being deleted. And actually, I guess that's a really good thing, because that means that now we don't leak threads until you kill the process. The threads actually get destroyed right away. Although here we have stacks for these threads still around. That's not right. We should do something about that too. Man, I'm so glad I added these views here to the to the process manager, because like I had the information, like the memory maps and stuff, it was in the proc file system, But being able to browse it here in Process Manager just makes it so much more discoverable. Like, honestly, like if I was doing this a month ago, I probably wouldn't even have noticed that these stacks are still around. So it's very cool. So let's try to get rid of them, but let's do one thing at a time. So let's see, what did we have here? Scheduler, did we change something about the scheduler? Oh yeah, right, fixing the bit rot. And this is an unrelated change, so let's undo that. So let's see, scheduler, runnables, git add schedulerino. Or actually, we can be a little bit good boys here. Write a good boy commit message. Runnables list have moved from thread to scheduler. It's a bit nice to say what you're doing and just a little bit of why. And then we have this stuff right here, right? So kernel delete non-main threads after finalizing them immediately. Previously we would wait until the whole process died before actually destroying or deleting its threads. This, I noticed this, or it doesn't matter. It's cool. Now we gotta deal with those stacks too. So let's figure out where we set up those stacks. I know that we're somewhere in the thread class, and presumably, let's just look for stack. Oh, stack. Something like create stack, Userspace Stack, something like that. Make Userspace Stack for secondary thread. Well, this is clearly the place to look. I love you past me for these extremely verbose names, because these things, like you can tell it, like I'm not always familiar with the code I'm reading, even though I wrote it myself, and it was somewhat recently. Stuff still falls out of my head, right? So it's really, really nice of my past self to do me this favor and name things so obviously and verbosely. It's something I really, really recommend strongly for anyone who plans to stay in a code base for more than a week, is to name everything extremely well, or at least try really hard to name things well, because it will pay you back. I mean, in a good way. Okay, so what do we do here? We allocate a region, and this just means that we're just telling the allocator, like, put this region anywhere. We don't care where in the address space it goes. And then it's the default Userspace stack size, which is 64K. And this is the name of that region, so those the names that we saw in the process manager. And then finally, the thread ID. It's just we're just passing it to string format. Sorry. Right. So we allocate a region, and it looks like we don't store that anywhere. So no wonder that it's going missing. So we store that in the stack pointer, the initial stack pointer of this thread. So this is going to be called during when we're constructing a new thread, I assume. Yeah. So here in syscreate thread, we create a thread object, and then we just tell it to make a Userspace stack. But then we allocate a region, but then we just throw away the pointer to that region for some reason. I don't know why we would do it that way, but it seems like we did. Probably because I was sort of copying this logic from how processes are launched. So when you launch a process, a process will always remember all of his regions. So when you tear down a process, or when a process dies, then all the regions will also go away. So this region here, for instance, it will go away when the process dies, because the process is the memory manager for the threads within that process, if that makes sense. But here, since the thread or the process may outlive any one of its secondary threads, we need to make sure that we track this region here so that we can get rid of it when the thread exits. So instead of putting it in a local, we're going to put it in a Userspace Stack region. Member and thread. So that will just be, where are you? Where are all the thread members? Here they are. Oh, see, we already have these for the kernel stacks. Region and Userspace Stack region. Cool. Now, the trick is that because we allocate this from the process, even though we keep a pointer to it now, the process is also going to have a pointer to it, because if you look here in allocate region, the way that it works is that first it allocates virtual address range, and then it creates a region and appends it to the mRegions vector. So mRegions is where all of the a process's virtual memory regions live. And this thing is what I was talking about that gets cleaned up on process exit. But we have to, when the thread exits, we have to make sure that we delete it from mRegions ourselves. So we have the allocate region here to help us with that. That's basically the one that we're going to want to call. So, and by the way, you can see here that the regions, it's not very efficiently stored here. We're just doing it's just a vector, so we're doing a linear scan to find the region that you're asking to deallocate. And then of course we also remove it, which removing from a vector, not the most optimal thing either. This thing should really be replaced by a different data structure eventually. I just used a vector because it was easy and allowed me to make progress, but eventually we should replace it with a something, I think like a red-black tree or something like that, so that we can have much better performance, but it hasn't been a problem yet, really. Anyways, enough talk. Let's call the allocate region. So the thread destructor. Here we will do mprocess dot deallocate region. See. So it should be safe to do all of these. Oh wait, what was it called? Userspace Stack. So it should be fine to deallocate these, and this is also like what I was saying about the finalizer. So we couldn't do this from within. If we're running in thread, that we couldn't run the destructor for thread, right? Because we would be on the kernel stack right now in this thread. So that's why it's important to have the ability to destroy something from the outside. That's something that I figured out the hard way. I should probably mention. At first, I didn't realize that I needed to do that, and then it occurred to me that like that's why things are not working. A lot of things in this system were figured out the hard way, but it can be really fun to figure things out the hard way. So it's not that I'm complaining, but I have spent a lot of time down the hard path. So I think this one can be null. So we need to null check that one before we call the allocate region. But these two guys, they're not going to be null. But I'm going to assert that they're not. It would be really... It wouldn't make any sense for these guys to not exist. because the Userspace Stack, or, well, actually, maybe every thread doesn't have a Userspace Stack, because you could have a kernel-only thread. In theory. So it's a good thing that I'm rubber ducking with myself here, or with you guys actually. I think it's absolutely the case that like making these videos has made me better at programming just by forcing me to always like verbalize what I'm doing and work through things in a very conscious way rather than sort of expecting my subconscious to find problems. I have to actually talk about what I'm seeking and stuff. It is very, very helpful. Oh, that's gonna take forever. Let's speed it up. So yeah, so this one, you should always have a kernel stack in every thread, because otherwise you wouldn't be able to start the thread. You would be able to start it because it starts in Userspace, but you wouldn't be able to exit the thread because you would have to call exit thread, which will take you into the kernel. So anyways, I suspect that we probably always do create a Userspace stack. I mean, I know that we did it here, but new thread, clone. I'm so curious how I've got this whole thing working out. Where's thread clone? Thread clone is for the main thread when we are doing a fork, right? And then how does the main thread get a... he gets his Userspace stack in exec. Alright. Well, anyway. I think everything is I was just going off on a curiosity thing there. So, okay, so let's see. Assertion failed. Kernel stack region. Well, shows what I know. So, let's see. Kernel stack region. We don't have one of those. Well, what the heck thread is this? Debug printf thread. It's this thread. It's the init stage 1 thread. Init stage 2, rather. Init stage 2. So init stage 2 is this little second thing that when the very first time we enter the kernel, we enter here in the init function, and then he sets up a bunch of things, and then when he's satisfied and thinks that he can start running threads, then he starts this thing called init stage 2, and then we continue initializing in that function. I'm not really sure if this is necessary or even makes sense. I think I just ended up making it this way because I was working on threading or processes, and it's like, oh well, I got to start a second process to do something, and then this came from that, so maybe this should stop being a thing. I don't know, but that's beside the point. Anyway, so the thing is with init stage 2 is that he eventually gets to the end here. At the end of init stage 2, he calls exit, and we never set up a kernel stack region for him. Okay, I'm just not going to question that right now, but instead I'm just going to say plop. So we'll only do it if these existed. That's fine. It's a good thing to add these assertions, because it's like you learn a lot of interesting things when your assertions fail if you're always adding assertions. I just learned that I don't know everything about this kernel. Okay, so here are the threads, and then let's pape braid PNG, and so we had the thread 2, and it's probably gone. And I don't see any. Can we sort by name? No, it's not sortable. Maybe I should make it sortable. Here's stack for thread 1. Can we just run the same thing again and again and get more threads? I think maybe we can. Yeah. Come here, Windows server. So it's the stack for thread 1, and then all the other stacks are gone. That's good. That's pretty good. And yeah, and of course, we can't see the kernel stacks here. And that's by design. Like, we don't expose that to Userspace. There's no need for him to see what kind of kernel stacks he has. The one thing I would consider is like having a separate statistic that would be something like how much kernel memory is used by this process or like is billed to this process, but we shouldn't be exposing like kernel pointers to Userspace. That's just not a good thing to be doing. Oh yeah, and down there we can see the decoded PNG. Maybe this thing should say like 3.6 M or something. I don't know. Anyways, seems like we were able to clean up those stack regions, so let's do a patch review. So here in the thread destructor, we now deallocate the various stack regions if we have them. And then when we make a user space stack for the secondary thread, then we store it in a member called the Userspace Stack region, instead of just keeping it in a local and forgetting about it. Then here's that member. So that's the whole thing. Cool. Kernel. Clean up thread stacks. Thread stacks when destroying, deleting, clean up thread stacks when destroying thread. When a thread dies. Threads should clean up their stacks when they die. Well, now it sounds like a bug report. Now it sounds like a fix. Okay. So let's do another good boy commit message. First, we were forgetting where we put the user space stacks for secondary. So added a member to space thread stack to keep track of that. Then in thread, we now deallocate the user space, kernel, and signal stacks, if present, for the thread. Stacks, yeah. Out of curiosity, init stage 2 process doesn't have a kernel stack, which I found surprising. Perhaps it should. Well, that doesn't matter. It was surprising, that's all. Okay, I think that's a pretty good commit message. Not forgetting about something, right? No. Cool. So maybe we'll just do a full build here just to make sure that everything's still working. Bless you, Ccache, for making my builds short again. When Ccache stops being enough, I have to look into some distributed compilation, but for now, Ccache is it's a breath of fresh air, I tell you. Okay, so let's see that one last time here. Ape. Which true PNG? What was that? It's one I was using for the WAV playback demo, right? So we don't see any other thread stacks. No, and we don't see any other threads here. So I think that we are good and done. It's cool. So if you made it this far, then I thank you for watching, for coming here and hanging out. I hope you saw something interesting. Today we did a little bit of kernel work after, I guess I've been doing a lot of GUI stuff lately and haven't been touching the kernel so much, so it's good to be back there. Yeah, thanks for stopping by, and I'll see you next time. Bye.